Let's start. So we are glad to have Losev from Yale. The title is Harish-Chandra Modules and Quantizations, please.
Thank you, Jan. All right, so what I'm going to talk about is some relatively modern take on a fairly classical story. And I want to start explaining this story. That's the motivation part, and I'm not going to be very precise, and I'm not going to essentially give definitions. So I start with a connected Lie group G. And what I want to do is to classify its unitary irreducible representations. So a unitary representation is a representation of this group in a Hilbert space by unitary operators. And there is some compatibility of topologies, which I won't need. Irreducible means that there are no stable closed subspaces. And I want to be very vague about these unitary representations because we are not going to see any in this talk. They are only here for motivation purposes. Now, if I want to classify them, I need to ask myself in what terms I want to perform this classification. And here is the idea which goes back to the work of Kirillov in the 60s, that I need to consider the following. I look at the Lie algebra, small g of the group G. Then, of course, the group acts on its Lie algebra by adjoint action. And therefore, it acts on the dual via co-adjoint action. And I can consider the orbits. They form a set. And I won't need anything from this set. It's just a set. Now, what Kirillov proved back in '61, and this is known as orbit method, is the following. So if you take a nilpotent group, for example, you can think about the group of strictly unitary angular matrices with real coefficients. Then, in fact, irreducible unitary representations are classified by coadjoint orbits. So given a coadjoint orbit, you can actually construct a unitary representation of the group G. And then almost immediately, there was the following question. Okay, so can we do it for semi-simple groups, which are arguably more interesting than important ones? And it's clear that we shouldn't expect a bijection. For example, when you have a compact group, to be unitary is the same thing as to be finite dimensional for irreducible representation. And so you have this, discrete set of unitary representations parameterized by highest weights. On the other hand, the set of orbits is still uncountable. Also, there can be no bijections. And there were attempts to fix this, which I don't want to describe in detail. Instead, I want to claim that orbit method actually fits into a bigger picture. And this is a picture of quantization. So quantization seeks to pass from a classical mechanical system to a quantum mechanical system. So let me try to explain how orbit method fits into this picture. So when in classical mechanics, we have a bunch of notions. For example, we have a notion of a phase space. This is where your mechanical system lives. And for classical mechanics, a phase space is a Poisson manifold. Let me call it M. Okay. Then we can talk about symmetry. And the symmetry is an action of a Lie group on M, which preserves the Poisson structure. And actually, you want a stronger condition. You want this action to come with a moment map, which essentially means that the vector fields associated to this action must come from functions on your manifold. And these functions incorporate into this map. And then you can ask, what does it mean for a phase space to have as many symmetries as possible, to be, in other words, most symmetric? Well, we are talking about group action, so perhaps most symmetric means that we have a transitive action of our group on a manifold. And because of this moment map condition, so the moment map exists, the phase spaces that can occur in this way, so those current transitive action, are of very special form. There is a coadjoint orbits. That's what we have in the orbit method here. And every coadjoint orbit is just a homogeneous space for the group G mod H for some Lie subgroup H and G. And you can go a bit more generally, namely you can consider equivalent covers of coadjoint orbits. Okay, so if you have an orbit G mod H, well, your H doesn't need to be connected. If it's disconnected, you can take a subgroup, say, of finite index, and then you have a finite cover. Okay, it doesn't need to be a finite index, but in our situation, it's going to be. And then we can talk about the same kind of objects in quantum mechanics. We can talk about phase spaces. A phase space is a Hilbert space. Symmetry is a unitary representation of a Lie group, and most symmetric means irreducible. And so what orbit method predicts is that you should have some kind of connection between most symmetric phase spaces in classical mechanics and quantum mechanics. In particular, if you start with a coadjoint orbit, or maybe its equivalent cover, you should be able to produce a reducible unitary representation. And that's what Kirillov's orbit method does for you in the case of nilpotent Lie groups. Now, what we are going to see in this part of the talk, and this part of the talk is about quantizations of algebra. Sorry, I forgot to mention this. So if you take a complex semisimple group, before we talked about real semisimple, but there is a special case of complex semisimple groups. If we are willing to make our life easier and consider quantizations algebraically, I'm going to explain what it means on the next slide. We still get orbit method as a bijection between equivalent covers of coadjoint orbits and certain quantum objects. Are there any questions at this point? All right, let me become more rigorous and actually try to define something. So my starting object is a finitely generated commutative algebra over the complex numbers, which I call straight A. And I wanted to come with algebra grading. So, you have, you decompose your algebra into the sum of direct sum of homogeneous pieces. And if you take an element of degree I and an element of degree J, you multiply them, you get an element of degree I plus J. That's what we mean by algebra grading. The grading is supposed to be by non-negative numbers, and the 0 degree piece is one dimension. So that's our starting object. For example, you can take, say, algebra of polynomials in finitely many variables with the usual grading. It's an example. Then I want to consider deformations of this graded algebra, and I want these deformations to be so-called filtered. So what does this mean? It means, first of all, that I have an associative algebra curly A, and I want this algebra to come with a filtration. So I still have a notion of a degree for an element, but I no longer have the notion of a homogeneous element. So still, if I multiply element of degree less or equals than I, and let's say less or equals than J, I get element of degree less or equal I plus J. And to be deformation means that I have a following isomorphism of graded algebras. So if I have a fielded algebra, I can form its associative graded, like so. So morally speaking, I just pick the top degree part of the product in consideration. So I form the associative graded, and I want to have an isomorphism with my initial graded algebra straight A. So this isomorphism.
Does it mean that you secretly assume that on your space, not very secretly, there is an action of a multiplicative group like C star?
On A, yes.
Yeah, on the spectrum.
That comes from the gradient.
Yeah. So then basically your deformation quantization, it's, I mean, your filtered deformations, it's kind of a very small part of this deformation quantization story.
Yes. That's exactly the case. So if I have a deformation quantization and I require it to be homogeneous, then I can pass to a filtered quantization like this by setting h bar equal to 1. Yes.
Okay.
Right. Okay. So that's a filtered deformation, and I can define an isomorphism of filtered deformations as follows. If I have two of them, pairs A and iota and A prime and iota prime. So I want this iota to be a part of the structure. Then isomorphism of deformations is a filtered algebra isomorphism phi, whose associated gradient intertwines the maps iota. Now, an important and very classical observation is that if we already know that group of A is identified with this commutative algebra, so this group is commutative, and therefore there is a positive integer d with the following property. When I take the bracket of A less or equals than I and A less or equals than J, I land in A less or equals than I plus J minus D. For example, D equal 1 always works, but sometimes higher values of D work as well. And once I fix such a positive integer D, I get a Poisson bracket on the associated gradient algebra, which is defined as follows. So the bracket of, the image of A in the associated gradient and the image of B in the associated gradient is the image of A and B of A bracket B in the associated gradient. And the degree drops exactly by D. So now if your A already had a Poisson bracket of some fixed, of some degree negative D, and iota here intertwines this bracket coming from the associative product with the initial Poisson bracket, then we say that A is a filtered quantization of straight A. Okay, so that's what I mean by quantization, and that's indeed a part of deformation quantization. I'll talk about more examples later, but let me first mention a very basic one. So I can take a finite dimensional Lie algebra, let me call it G, and I can form it symmetrical. It's a graded algebra. It has a Poisson bracket coming from the Lie bracket on G. And it has a very well-known quantization, the universal enveloping algebra of G, where G sits inside of here. And the relation for the universal enveloping is that the commutator of two elements of G inside of the universal enveloping is the same thing as the commutator in the Lie algebra G. So the reason to give this definition is that a representation of the algebra G is the same as the representation of its universal enveloping algebra. Are there any questions?
So your I understand that this action of C star is very, very important. And probably my question is sort of perpendicular to what you're going to explain. But so it's probably just a remark that you can generalize orbit methods in a different direction when you allow the group G to have a non-trivial Poisson Lie structure. And then the orbit method, these coadjoint orbits, they are kind of, in more general story, these are dressing orbit actions. And so if this Poisson Lie structure is trivial, then you get this Kirillov story. And of course, it's not a filtered quantization in your sense, but still it has some kind of symmetries which kind of people, at least physicists, use. Yeah, like for example, the question is about classification of irreducible unitarizable representations. Also appear in that story, but probably it doesn't have kind of as complete answer as in your story, probably.
I see. Yeah, okay, thanks. All right, indeed. So let's talk about classification. And it's not possible to classify quantizations, in simple terms if I don't put any assumption on my algebra A. So I want to put some assumptions. And well, A is finitely generated, so I can form the spectrum of A. It's algebraic variety or algebraic scheme more generally. And I'm going to put a very restrictive assumption on this X. So I want it to be singular symplectic in the sense of Bobel. It's also known as having symplectic singularities. So let me explain you what this means. So first of all, I want this X to be normal as a scheme, in particular reduced. Second, well, I have a +1 structure on X, and I can restrict it to the smooth locus. I denote it by X-rec. I want the structure to be non-degenerate. I want this to come from a symplectic form, algebraic symplectic form on X. Let me call it omega rec. Okay. And then I want this form to lead to some resolution of singularities. So namely, there is a resolution of pi from X tilde to X. So X tilde is smooth. And I want on X tilde to form omega tilde. I don't want it to be symplectic, just an algebraic to form, whose restriction to the preimage of X-rec is this pullback. Okay. So that's a condition.
So I heard the word symplectic resolution of singularities, and this is not, because
this is
you do not have, you don't have symplectic structure on X tilde.
Right.
Okay.
So symplectic resolution is a special case. Every variety with every Poisson variety with a symplectic resolution is singular symplectic, but not every singular symplectic variety has a symplectic resolution.
Okay, so and you need it probably because you will consider something like closures of orbits or something like that.
Yes.
Yeah, which do not. Okay.
Yes. So in general, well, I mean, normalizations of orbit closures are singular symplectic, but they may fail to have a symplectic resolution. There is a classification. So if symplectic resolution of such a variety exists, it's a cotangent bundle to partial Bloch variety. So it's an orbit of very special type. We'll get to some examples a little bit later. All right, so let's assume that we have this condition that X is singular symplectic, and then you can, in fact, have a very simple classification of quantizations, which is due to myself back in 2016. Namely, we have a finite dimensional vector space, which I will call H sub X. And we have a crystallographic reflection group, which I will call W sub X, acting on H sub X, such that filtered quantizations of A up to isomorphism are parameterized by points of the quotient in a rational way.
May I ask you a question about this really nice theorem? So in deformation quantization, there is, in the case when X tilde is really smooth symplectic, there is this Deligne class, which is basically a formal path in the second cohomology. So how this theorem kind of fits in this non-homogeneous, I would say, setup?
It fits very well. So
glad to hear that.
What's going to happen is this. So this variety is singular, and therefore we would kind of try to pass to a variety which is more smooth. If we have a symplectic resolution, we just take a symplectic resolution, and then we can, we can quantize it essentially by using what you said. This was done in algebraic setup by Bezrukhavnikov and Kaledin. All formal quantizations are going to be classified by second rank homology, well, formal power series. Filtered quantizations, meaning that your quantization is homogeneous, are going to be classified just by second homology. You just fill all terms of
just constant, no higher corrections. But what is WX? So this is
and then if you want to have quantization of X out of quantization of a resolution, you need to pass to global sections. And this glues
okay.
different quantizations together. And
I see,
the way how it glues is precisely the section.
I see, because you want an algebra, not a sheaf of algebra.
Yes, that's it.
Okay. Mm-hmm.
Now, in general, there is no symplectic resolution, so you do something different. So you take a maximal partial Poisson resolution. Its singular locus is codimension at least 4. You remove the singular locus, and you do the same thing as what you would do with a symplectic resolution. And it works. Thanks for the question. All right. So let me show you some very classical example. So let's take the Lie algebra SLN. And let's take a partition mu of n. Okay, then to this partition we can assign a nilpotent orbit in G, and G is identified with G dual by trace pairing of Jordan type mu. So for example, if your mu is this 3, 1, then O is just a conjugacy class of this Jordan matrix. So here is a block of size 3, here is a block of size 1. Then what I'm going to do, I'm going to define my algebra A to be functions on this orbit. In this case, we are kind of fortunate because the closure of the orbit is normal. So one can show that this algebra is actually the algebra of functions on the orbit closure, and therefore X is this orbit closure. Then this algebra is graded because one-dimensional torus acts on G and fixes the closure. And so it gives you, grading of the algebra of functions. And one can easily establish that this variety X is singular symplectic. It's even better, it has a symplectic resolution. So what you do is this. So take your partition mu, then transpose it, and take the corresponding Levy and parabolic subgroups of SLN. For example, if I start with 3, 1, then the transpose is 2, 1, 1. And the Levy that I pick has blocks, it's block diagonal matrix with blocks of sizes 2, 1, 1. And P is the corresponding block upper triangular matrices inside of SLN. Then what I can do, I can form the cotangent band, G star G mod P. And the way to how I can look at this is the following. So it's a homogeneous vector bundle on G mod P with fiber n. And n is just the nilpotent radical of the parabolic subalgebra, which is the Lie algebra of capital P. So it will consist of, all kind of, it's matrix entries which occur in P but not in L, allowed to be whatever you want. Okay. And then you have this nice morphism, which can be described as follows. So what is a homogeneous bundle? So you take G times N, and on this variety, you have a diagonal action of P. So P acts on G from the right, it acts on N just from the action by conjugations. And this homogeneous bundle is a space of orbits for this action. In particular, when G is an element of a group and N is an element of this Lie algebra, I have the corresponding element in the homogeneous vector bundle. And I send this element to G and G minus 1. One can show that it lies in the closure of the orbit O, and the corresponding morphism is in fact a resolution of singularities. And it's a symplectic resolution of singularities. Okay. Are there any questions here?
So Springer resolution is a special case.
Yes.
Okay.
Springer resolution will correspond to the case when parabolic is a barrel. This partition is just a single part, and X is just an important part. And here I have a parabolic version of this. All right, so let me discuss how to construct quantizations. So first of all, in my theorem, I had the space H sub X, and I had the crystallographic reflection group W sub X. Let me explain who those are. So H sub X is the characters of the Levy subalgebra, and geometrically it's second cohomology of G mod P or of T star G mod. And then this while group is just the quotient of the normalizer of the levy by the levy. So if we look at the previous page, so the space of characters of L is three-dimensional. It's the number of parts in mu transpose, or the largest part in mu. And then the normalizer of the levy, modulo of the levy itself, has two elements, which permute these two blocks. Okay, and so this while group is going to be that much to that.
So
okay.
What is it geometrically? Because it's kind of mixture of languages. H of x is indeed second cohomology, but W of x is something which is not immediately
right. So you can describe this while group geometrically in terms of geometry of this x, not in terms of geometry of x tilde. And maybe at some point, do you guys make a break?
No, normally we don't.
You don't. So roughly speaking, what you do kind of the following thing. So this x will come with a number of codimension 2 diffs. This number is finite. Then you take slices to codimension 2 diffs. They have dimension 2. They're symplectic singularities. They're Kleinian singularities. Kleinian singularities are classified by simply laced Dynkin diagram. So let's take the corresponding while groups. Okay, so for each codimension 2 diff, I give you a simply laced while group.
So then if my
this
x,
is,
there is probably, you have example.
So in this example, in the examples that we consider here, we have one codimension 2 orbit, which is 2, 2, and the corresponding singularities of type A1. And so that's why I get a while group that much to that.
Yeah.
But then kind of, then you need to do something more. So, so what's going to happen is that this is not the answer, and you need to take certain fixed points of monodromy inside of this while. So that's not going to be very much relevant for this talk, but maybe I can explain in more detail later after the talk. All right. So how do I construct a quantization? Let me pick an element lambda, which is a second cohomology class on G mod P, and I'm going to construct this quantization A lambda. So and do the following. So let me take the following element, rho sub GP, and it's 1/2 of the first Chern class of the bundle of top forms on G mod P. And here is an explicit formula. Okay, I sum all roots of G, which correspond to n, and then I multiply by -1. Then, from this, I can form the sheaf of twisted differential operators, which I denote by this. So, who are those? So, if this twist is 0, then I talk about usual differential operators. If it's the Chern class of a line bundle, I talk about differential operators acting on this line bundle. And in general, you don't need a line bundle. You just need kind of a complex line bundle. And this is this sheaf of twisted differential operators that I have in mind. And it quantizes this non-affine variety x tilde. Then, as I explained in answer to Jan's question, to pass from quantizations of x tilde to quantizations of x, I need to take the global sections. And that's a filtered algebra where I take filtration by the order of differential operator. Then it turns out that if two parameters are conjugate by the action of lambda, by the action of this group W, then these quantizations are the same. And so I get, in fact, so I constructed quantizations parameterized by points of the quotient, and it turns out that there are no others. Okay. So let me show you a somewhat different example. let me take a principal orbit in SLN. It's a single Jordan block. And it has a non-trivial fundamental group. The fundamental group is Z mod NZ. Then what I can do, I can take the universal cover or tilde of this orbit. I can take polynomial functions on this cover and take the spectrum. Turns out that this is singular symplectic. And when n is equal to 2, this variety is actually very simple. Namely, O tilde is just C2 without a point. And therefore X is C2. It's symplectic and actually smooth. It has only one quantization, which is the first while logic. So that's very easy to construct. In the gel case, the life is more complicated. Namely, this affinization of the spectrum is not smooth. It doesn't have symplectic resolution. One can show that there is still only one quantization. So the space H sub X is 0. And I'm not really sure how to construct it explicitly. But the general theory tells you that it's unique. And then, of course, we can carry this over outside of type A. Namely, if we have a semi-simple algebraic group, then it's the algebra identified with its dual. I can talk about nilpotent orbits. Let's say O, it's orbits which are represented by an nilpotent matrix in a faithful representation. I can talk about equivalent covers. Both classification of orbits and classification of equivalent covers is known in all cases. And I can take the algebra of functions on equivalent cover, can show it's finitely generated, graded, and Poisson. And I can play the same game as before. So the spectrum is singular symplectic. I can run the classification theorem as before. We know in all cases how to compute the space and the group acting on this. And so we get a complete classification of quantizations in this case, in explicit terms, explicitly theoretic terms. Are there any questions? Okay. From this classification, one can deduce the following theorem, which is this algebraic version of the orbit method, which I promised, which was conjectured by David Vaughan back in the 90s, I think. And it's the following theorem by myself, Lucas Mason-Brown, and Matvieievskyi in the book that we have discussed in the very beginning. So I start with an arbitrary semi-simple algebraic group, let's call it G. And then there is a natural bijection between the following things. So on the classical side, I have G equivalent covers of all coadjoint orbits. So in that discussion of the classical orbit method, so what are those? Those are all most symmetric phase spaces in classical mechanics, where the symmetry is this semi-simple group. And then they're in bijection with quantum objects. So these quantum objects are quantizations of the algebras of the form C of O tilde for all covers O tilde of all nilpotent orbits. Okay. So this is my collection of quantum objects. I take all covers of all nilpotent orbits, and then I construct their quantizations. And these two things are in a natural bijection. And under this bijection, you can ask, okay, so what happens when I start with O tilde? Equivalent cover of a nilpotent orbit. Then, perhaps not surprisingly, I'm going to get a quantization of O tilde, which has 0 parameter. So H of X is naturally a vector space, and there is a distinguished point called 0. That's so-called canonical quantization. It plays a distinguished role in this story, as I will mention a little bit later. Questions?
So it's a question sort of about the logic, because I understand that the orbit method was designed for describing, as you explained, some unitary irreducible representations, which means that you start with the quantization of the whole space, whatever this algebra or filtered algebra is, and then study for the beginning without unitarizability, just irreducible representations. But here, kind of, you say that algebraic methods, you start with whatever you call most symmetric orbits and you quantize them.
Right.
It's sort of like, you know, kind of, you achieve the answer which you know from the very beginning, because it's kind of more naturally would be just to describe in the big quantum algebra the probably primitive ideals, yeah, such that the quotient gives you two-sided primitive ideal, such that the quotient gives you the quantization of this C of O tilde or something like that.
Right. So this algebra that I get are going to be very closely related to the universal enveloping algebra.
Yes, so it's basically yeah.
So here, kind of, you try to. Well, I mean, what's kind of ideological point of deformation quantization? Is that I try to solve my quantization problem in two parts. I first produce this quantum algebras, and then I try to consider some representations. And we'll get to representations in like literally now.
Yeah, but you do not claim here, I mean, if you study representations of the enveloping algebra, then that's okay, they are clearly related to some orbits. But if it just, you know, your, let me call it just, I get you, symplectic resolution, although it's not, then it's kind of something else. You do not know what's the most symmetric. If you are kind of quantize a symplectic resolution and want to describe irreducible representations, so probably some more work needs to be done.
That's right. I'll pass to representations in a second.
Yeah, okay.
All right, let's do it. Let's now we have, you know, we have an algebra and we have this nice quantizations, and we should try to understand some modules of those quantizations. But again, let me try to talk about motivation first and tell you another part of very classical story, which actually goes back to Harish-Chandra, and it's the 50s. And in this story, I'll start with a real semi-simple Lie group, and it has a maximal compact subgroup, which I call G sub R and K sub R respectively. Then I can take the complexification of the Lie algebra of G sub R, as well as the complexification of this compact group. I just call it K. Some examples. For example, the most basic one, well, let me start with SLN R. Then the maximal compact is SON R. The complexification of the Lie algebra of GR is SLNC, and then the group K is SONC. So this group has a little issue. It's not simply connected. I can take its simply connected cover, and if n is bigger than 2, then the simply connected cover is twofold. The group K sub R is the real spin group, and its complexification is a complex spin group. Or I can take the group which is already complex, SLNC. Then its maximal compact is SON. When I complexify the Lie algebra of SLNC, I just get the two copies. And K is the diagonal copy of SLN. In this setting, we can talk about so-called Harish-Chandra GK models, which is following object, it's a module over the algebra, which is required to be finitely generated over the universal enveloping algebra, and such that the action of the Lie algebra of the group K, denoted by this funny symbol, actually integrates to the group. For example, if I take a finite dimensional representation of, let's say, simply connected complex group G, then it's automatically Harish-Chandra. But there are interesting infinite dimensional representations of this form. And here is an example. Let me take a universal enveloping algebra and mod out by the left ideal generated by K. So the group K acts on U of G by adjoint action, and this gives you the required action on this module. The case when your real Lie group is complex is distinguished. So in this case, as in the examples that we have seen, the Lie algebra G is two copies of, well, I should say GR, which is still a complex group. Here I have the diagonal embedding. And we can convert a module of two copies of G into a bimodule over the universal enveloping algebra in a standard way. Then this integrability conditions that we have imposed just tells us that the adjoint action of G, just action by commutators, so the G can act on the left and on the right, and you can take the difference. It's the adjoint action. We wanted to integrate to the group G. And the corresponding bimodules are called Harish-Chandra bimodules. They're kind of nicest Harish-Chandra modules, although they're not the easiest. And the reason why this definition was introduced by Harish-Chandra is that he wanted to have some algebraic framework for talking about unitary representations of a group. So it makes sense to talk about unitarizable GK modules. Unitarizable means that you still have a Hermitian scalar product, and you wanted to have a certain invariance property with respect to the action of G. And then Harish-Chandra proved that if you take irreducible unitarizable Harish-Chandra modules, they are in bijection with unitary representations of the group. So what you roughly speaking do to go from right to left, you take vectors which are locally finite for the action of the maximal compact subgroup. It's a dense subspace. And then if you want to go from left to right, you need to take some kind of condition.
Just graduate students probably, they are infinite dimensional kind of typically.
Yes, so if your semi-simple group is not compact, it has very few finite dimensional unitary representations, essentially only the trivial one. So you need to look at interesting one, meaning infinite dimension. And so most of irreducible Harish-Chandra modules will be infinite dimension as well. Okay, so that's a classical motivation for what I'm going to do, but what I'm going to do is something different. So let me explain what is kind of the goal of my story. So I start with the same framework as before. So I have an algebra of functions on a singular symplectic affine variety, and I want this algebra to be graded. I pick a quantization parameter, let's call it lambda, and I can form a filtered quantization as before. So what I want to do is to quantize, in a certain sense, suitable singular Lagrangian subvarieties y in X. And for certain Lagrangian subvarieties, I'm going to get what I will call Harish-Chandra modules.
Yeah, I understand that it's informal description. Now, these singular Lagrangians, will they be kind of C-star invariant?
Yes.
Good. Do you take only, hold on, Lagrangians, or maybe rank one, I'm not sure, rank one local systems on them, or maybe, let's see.
Okay, yeah, shall I explain what's happening? Okay, so who are the Lagrangians? So what you're going to do, you will take an anti-Poisson involution of your algebra, which is graded, okay, which preserves the grading. So take an anti-symplectic involution and take the fixed locus in X. In the smooth part of X, you will get a smooth Lagrangian. But this locus is going to have some singularities. And that's why I'm talking about singular Lagrangians. If my X comes from a cover of a nilpotent orbit, this Lagrangian is going to be a union of K orbits. And if I quantize this Lagrangian in a proper way, then I get a Harish-Chandra. Now, what am I going to quantize? This question is a little bit subtle. So I know what it is on a smooth locus, and it's indeed a twisted local system. It doesn't need to be of rank one, although in many cases it is. Then it somehow needs to extend to the singular locus, and that's where all the complications start to arise.
Oh, great. But hold on. You see, there is some intuition from symplectic topology, probably. I'm not sure whether it's applicable to your story. Probably Lina knows, and maybe other people, with this Lagrangian skeleton, which means that it should be a sort of a perverse sheaf on the whole thing. In your story, is it the case? Will you need extensions to Y of your local systems?
Yeah, I'm not sure.
All right.
How it
Will they be
perverse
then?
It's kind of what they more. Okay, so somehow in this story, what they should morally extend to, although sometimes it fails, they should extend to Cohen-Macaulay models.
Look, sounds scary because it's not geometric. I do not see. You see, basically, there is kind of a very general philosophy which does not take the cis-direction into account. And it's kind of says that there is an equivalence between the category of holonomic modules or the quantized algebra and the Fukaya category of the same space, but your X or X tilde, it's assumed to be smooth. Y can be singular, that's okay. But the whole space has to be smooth. And then from this perspective, irreducible modules, irreducible holonomic modules means supported on Lagrangian, they should correspond to irreducible objects of the Fukaya category, which probably in the case when Lagrangian is smooth amounts to reducible local systems. Yeah, which agrees with your hope, but ignores C star. Probably it's kind of more flexible because there is no group. It's kind of deformation, quantization, business, and Fukaya story. Yours is more complicated. All right, okay, thank you.
Right. So, all right, we want singular Lagrangians, but somehow if they're two singulars, then it's very complicated. What I want this Lagrangian to be reducible, and I want the codimension of the singular locus to be big or equal than 2. And then somehow, under further more minor restrictions, one can do classification. And irreducible modules are going to be classified by setting irreducible local systems, or maybe twisted local systems. So sometimes you have a twisted local system on the regular locus, but it does not correspond to an actual module. So that's an interesting feature of this story. So how is this connected to the classical story? Well, I will need to take the setup where my algebra is functions on a cover of an nilpotent orbit. In particular, the group Gx here, it's a Hamiltonian action, it has a moment map. And I can, it turns out I can lift it to a quantization. So Gx on quantization A lambda. And moment map quantizes as well. I have something called quantum moment map. And it's a G equivalent homomorphism of Lie algebras from the Lie algebra of G to the subspace, which is actually a subalgebra in A lambda, all elements of degree less or equal than D, when minus D is the degree of the Poisson bracket on A. And then the condition of the moment map says that the joint action of G on A lambda is just a differential of the action of the group on the algebra, which does, this action doesn't know anything about phi. And so phi is this homomorphism. All right. So because of this homomorphism, every module over A lambda is also a module over G. Now, if I choose my Lagrangians carefully, as I explained in answer to Jan's comment, the Lagrangian is going to be a union of orbits for this group K. What I'm going to get is a Harish-Chandra module. So what kind of collection of Harish-Chandra modules do I get? That's, you know, it's not that there is an intrinsic characterization, but experimental evidence suggests that Harish-Chandra modules that I get are often unitarizable. So they correspond to some unitary representations. And moreover, many interesting unitarizable Harish-Chandra modules arise in this way. So I don't deal with this unitary representations, but I deal with kind of objects that should be closely related. Okay, there should be a large intersection. Although there are, you know, norm is contained in those. And checking unitarizability is hard. It's not something that we do even in that, well, I mean, in that 200-page paper, we are heavily based on previous results by other people to check unitarizability of what we get. So in the remaining whatever number of minutes, we can negotiate that later, I'm going to concentrate on a very special case, a case of bimodules. That's a nice case. With Schilling U, we have worked out classification of irreducible Harish-Chandra modules over this algebras A lambda, which arise as quantizations of fairly special nilpotent orbits. So these are nilpotent orbits O in G, not covers, with the following codimension condition. I want the codimension of the boundary to be big or equal than 4. It covers many interesting cases. For example, it covers almost all so-called rigid orbits. Partial justification for this restriction is this. So the Lagrangians that I care about are going to be the following. So I take the closure of O and intersect it with the orthogonal complement to the algebra K. It's a union of finitely many K orbits. And every K orbit in here is a Lagrangian subvariety of the corresponding G orbit. Proof, it's actually the fixed point locus of an anti-symplectic involution. So the codimension here is big or equal than 4. So the codimension of the boundary here is big or equal than 2. And that's the setting where I want to work. Okay, are there any questions?
So I'm kind of constantly confused when you jump from the Lie group framework to the arbitrary, let's call it symplectic resolution framework. But now you will be talking only about quantizations of the coadjoint orbits,
Yep.
or it's more general.
Huh? It turns out that these notions of Harish-Chandra modules and bimodules, they carry over to the general case.
Ah, Okay, so
they're not as nice as, especially in the case of arbitrary modules. The case of bimodules is still very nice. The case of model Harish-Chandra modules is not nearly so nice as the least theoretic case, but you can still talk about it.
Okay, great.
All right, so how much time do I have?
Well, you just continue. I mean,
Okay.
So you can go over the time. It's
All right.
I told you it's a very democratic state, although it's
All right.
Republicans. Okay, go ahead.
All right. Okay. Okay, so I want to explain you what I means by Harish-Chandra bimodule, so a quantization of an arbitrary singular symplectic variety with this gradient. Okay. So my axis, or general singular symplectic, such as algebra of functions, is positively graded. And I fix a quantization A lambda. So that's the definition. Here is the definition. A bimodule over A lambda is called Harish-Chandra if it comes with a filtration by just C subspaces, like so, with the following three conditions. So first of all, this is a bimodule filtration. It's compatible with the filtration on the algebra in the only possible way. Second of all, okay, let's look at the bracket of an element in algebra of degree less or equals than I, and an element of the bimodule of degree less or equals than J. So by this condition, it will lie in degree less or equals than I plus J. But I actually wanted to lie in the degree less or equals than I plus J minus D, where D is still the minus degree of Poisson bracket on A. And we've seen this condition before. It's a condition on the filtration of A itself. So in that condition, I want the Lie bracket to have degree less or equals than minus D. And I impose the same condition here. But instead of an algebra, I consider an arbitrary bimodule. And finally, I want this bimodule to be finitely generated. You can ask me about an example. And in this setting, examples are not so easy to come by. A lambda itself is a Harish-Chandra module. Every two-sided ideal, every quotient by a two-sided ideal is a Harish-Chandra bimodule. Constructing more examples explicitly is not easy.
So if I deform the diagonal kind of as a Lagrangian submanifold and then quantize it, it will be sort of a kernel, and it gives an example of a bimodule.
Yeah.
Okay.
Yeah. So let's see. What it has to do with the diagonal. So first of all, condition 1 just tells you that the associated graded is a bimodule over the undeformed algebra A. Condition 2 tells you that the left actions of A on the left and right actions of A on B coincide, because when you pass to associated graded, this bracket becomes 0. So group of B is a module over A, not just a bimodule. It's a bimodule where the action is there. And finally, 3 just implies that group of B will be finitely generated. Sorry, I actually need to apologize. That's a typo. So it's the associated graded that needs to be finitely generated as a bimodule. Otherwise, the filtration doesn't work. Let me fix it. Okay. And what we can say is that B then quantizes in the certain sense a very easy Lagrangian, which is a diagonal one, X inside of X times X, where here we take the opposite Poisson bracket. And now, as usually happens with quantizations, group of B is not just a bimodule, it's not just a module. It inherits more structure. And the structure is a Poisson structure. So I have a bracket between an element of A and an element of group of B given by this formula, which also should be familiar. in the case of algebra, this is how the Poisson bracket or the associated bracket was defined. So now we do it with arbitrary bimodules. Questions here? Okay. I want to state a classification theorem for irreducible Harish-Chandra modules, and actually a little bit more. For this, I will need two facts. The first fact is that, and this fact is due to Dmitry Koledin, is that X has finitely many symplectic leaves. So what it means in practice with this, so you have the regular locus, which is symplectic. Okay, you remove a regular locus, what you get is a Poisson subvariety. Then the regular locus in that Poisson variety in the singular locus of X is symplectic, and then you repeat. Okay, and on each step, the regular locus is symplectic. And then this connected components of the regular loci are the symplectic leaves. And the first fact and the second fact is this. So you can ask, okay, so what is the fundamental group of the regular locus? And it's conjecture that it's finite. This conjecture is not known. What is known is that the algebraic fundamental group, which is a profinite completion of the usual one, is finite. In particular, this algebraic fundamental group is not just the profinite completion, it's a quotient of the usual fundamental group, because quotient gamma. And this was proved by Namikawa. Let me give you an example where these claims are easy to see. So let's say that X is the closure of a nilpotent orbit. That's an examples that we've seen in the first part. And then the leaves are exactly the G orbits in X. It's classically known that the number of nilpotent orbits is finite. Now let's have an example for the second statement. And let's take X to be the spectrum of algebra functions on some cover, O tilde. That's a homogeneous space G mod H. And then the entire fundamental group of O tilde is finite. It's just the component group of H. Okay. And in fact, the algebraic fundamental group is just this fundamental. And the usual fundamental group of extract as well. So this is manifestly finite in this example, and the fundamental group is finite in all examples where we are able to compute it. So why do I need this group? Because it will give me a classification of at least some Harish-Chandra, some reducible Harish-Chandra modules. And here is a theorem that I proved in 2018. Which says that there is a functor from the category of Harish-Chandra A lambda modules denoted as such to the category of finite dimensional representations of gamma. This functor is full, this functor is exact, and this functor is monoidal. If you have two Harish-Chandra modules, you can transfer them and get a Harish-Chandra module. And for this functor, we can describe its kernel, meaning the objects that it kills. We can describe its essential image. So what it kills is all Harish-Chandra bimodules B with associated greatest distortion. And here is an important remark. So this filtration that I take in the definition is not unique. There are multiple filtrations. Satisfying the properties described here. Okay. Nevertheless, the property that the associated greatest distortion is independent of the choice of the filtration. And so I have a well-defined subcategory. Now that's actually the statement about the kernel is easy. The hard statement is about the image. So the image is going to be all representations of gamma which vanish on a certain normal subgroup. So this is a general statement. And then the deep part of the statement is that one can actually compute this normal subgroup starting from the quantization parameter if one imposes certain minor assumptions on this variety X, which I will mention in the proof. Before I get there, are there questions?
Yeah, I'm trying to understand what's written. So your Harish-Chandra bimodules are end functors from some category. And for you, what this category should be?
That's a good question. You can certainly tensor whatever representation of your algebra you want with a Harish-Chandra module, Harish-Chandra bimodule. But somehow, let me put it this way. I think that this the situation with Harish-Chandra bimodules is rigid enough so that you don't need to use this language, if this makes sense.
Mm-hmm.
So somehow, you see, in the end of the day, when I mod out my category of Harish-Chandra modules by a certain subcategory, it has a very simple description. The category of representations of a finite group.
Yeah, but if, for example, gamma is trivial, just imagine. So
I have the only irreducible Harish-Chandra bimodule with this condition, and this irreducible Harish-Chandra bimodule is the minimal ideal in the algebra.
Yeah, but your sort of a fiber functor, it's a functor to the category of vector spaces or what? Just forget about, yeah.
I'll give a kind of a construction of this.
Okay. Mm-hmm. Thank you.
So one question that one can ask, and that's actually a very interesting question, is, okay, so here I describe a abelian category for you. So what happens if I try to describe derived category, which will mean kind of derived category of all bimodules with Harish-Chandra?
Yeah, which looks natural since you deform the diagonal, probably.
Right.
You have some D modules. Do you have some, I don't know,
and I don't know
regular singularities or something like that?
Yeah, we'll get there, but I don't have a good answer to this question.
Yeah.
So one could kind of try to ask what it is if we just consider the smooth locus, but it's not quite the right thing to do. And I don't know what kind of contribution singularities make.
Yeah.
So this proof kind of what this proof tries to do, and I hope it succeeds, is try to understand the role that singularities play when we try to understand objects in the abelian category. For right category, I don't know the answer.
Okay.
All right, so let me sketch this proof. And I'm going to give you a cheating construction of this function. So the construction that I'm going to give you just tells you what the functor does on the level of objects. It doesn't tell you what it does on the level of morphisms, but in the end of the day, we sort of don't expect that many morphisms in our category, so it's okay. And we do kind of what perhaps should do. In this situation, so we have a B. It's a modulo of non-commutative algebra that we don't understand. Well, we can take one of the filtrations that we have on this module, which exists by the definition, take the associated graded. It's now a Poisson modulo of a singular symplectic variety. It's still complicated. Let's restrict to the regular locus. And what we get is a coherent Poisson modulo over the structure. But now, this X-rack is a smooth symplectic variety, and for such a variety, Poisson module is a more familiar thing. It's a D module on X-rack. So where, when you convert brackets with functions into an action of vector fields. Okay, so I get a coherent D module, and you see this thing here carries cis direction. And because of this cis direction, what you get has regular singularities.
How do you see that?
How do I see this? That's because on the algebra of regular functions, the gradient is positive.
Okay.
And then you essentially, your situation is a column.
Okay. All right. Yeah. Okay.
All right. Now a D module with regular singularities gives me a representation of the fundamental group. But this fundamental group, its profinite completion coincides with it has maximal finite quotient. And because of this, any finite dimensional representation will just factor through this finite quotient. All right. So I started with a Harish-Chandra bimodule. I got a representation of this algebraic fundamental group. That's what I wanted. That's not quite a function. So that's not quite a construction. It's just a description of what happens in object. You can give an alternative construction, which is more technical, which will show you that you have indeed a functor. This functor is exact, this functor is full, and this functor is monoidal. But it's much more technical. I'm not going to explain this. What the explanation that I gave shows is that the kernel is as what we described. So all modules will associate graded distortion. Then there is a question about the image. How do we describe the image of this function? And you can see from essentially general principles that this image is going to be representations or just representations of some quotient. That's easy to see. The question is, how do we compute the quotient? And one can show that it's generated as a normal subgroup by some loops around codimension 2 leaves. So, you have your variety X. It's singular, you remove the singular locus, you can still talk about loops in extract which go around codimension 2 leaves. That's well defined up to conjugation. And you need to pick some of these loops. And then you need to determine which loops you need to pick. And you can imagine that this question will just reduce to what happens on the slice, to a codimension 2 leaf. It's sort of, it localizes to a small neighborhood of the of pointed codimension 2 leaf, and then to a slice to this leaf. We take leaves of codimension 2, the slices are going to be Kleinian singularities. And so we essentially reduce to the case when we have dimension 2. And then our question can be solved when X is not of type 8. What happens is that all Kleinian groups except 8 are solvable. And when the Kleinian group is solvable, I actually completely describe Harish-Chandra bimodules over its quantization. It's some least theoretical limit. Okay, so but what's important? So what's happening with this proof? So you start with you start with this guy. It's local system on extract. You then can always quantize this local system to a module over quantization of extract. But you don't want to have something over quantization of extract. You want to have something over quantization of X. So you need to extend this quantization to X. And what I'm telling you is that it's enough to extend it to codimension 2 leaves. And then this extension just is controlled. The possibility of extension is just controlled by what happened on the slices. Okay. Are there questions?
It's really nice argument. So yeah.
And so somehow the purpose of this story is like this. So in a more general situation where you try to quantize singular Lagrangians, you are okay on the smooth locus, where you have some twisted local system to quantize. It's known how to do this. Essentially, they always quantize. And then you want to push it to the entire Lagrangian. And you essentially, modulo some technicalities, which have to do with Cohen-Macaulay, need to push it to, well, assuming your singular locus has codimension 2, you need to push it to codimension 2 strata in the singular locus. And this is, you can hope that it's controlled what happens on the slices. So that's a general picture of what myself and my collaborators were able to do with this quantization problem up to this point. All right, but let me finish by discussing a special case. And the special case is when the quantization parameter is 0. And this case is particularly nice. That's a so-called canonical quantization, which enjoys several very nice properties. For example, in all cases where I can check, and this includes algebras of functions on nilpotent covers. So myself and my collaborators wrote this 200-page paper, and like half of it, almost half of it, has to do with this proof. This algebra is simple. In the cases of interest, we don't do all cases. Then my collaborators wrote a separate paper where they handled remaining cases. And that's this requires a lot of work. It's there should be some conceptual argument somewhere, but we are only able to do it case by case. But now, if we know that this algebra is simple, then the kernel of our functor is 0. And we just have completely described Harish-Chandra bimodules by this theorem. But also the description of this normal subgroup is particularly nice. In this case, it's generated by all loops around codimension 2 leaves. In particular, we can completely compute it in these cases, in cases of covers of important orbits. And then, okay, so we get some Harish-Chandra bimodules out of this. One can show that they're completely reducible over the universal enveloping algebra. And we can completely describe all the reducible summations geometrically. And they are called unipotent bimodules. Getting back to where we started. So we have started by talking about the orbit method. And the orbit method was supposed to classify unitary representations. So one can show that these bimodules, there's a Harish-Chandra bimodules for G, are unitarizable when G is a classical group. Well, the Lie algebra G is classical. This requires some construction of these bimodules plus some long results about classification. We don't do any independent unitarizability checks. Conjecturally, these bimodules that we get are always unitarizable. Currently we have software called Atlas, which checks unitarity of Harish-Chandra modules, and the software is not powerful enough to deal with, I think, Harish-Chandra bimodules over E8. So complex E8 is too complicated for the software to check. But conjecturally, the bimodules we get are unitarizable, and they should be thought of as the following. So orbit method tells you, okay, let's take a nilpotent orbit and produce. Let's take a quadrant orbit and produce unitary representations. So what these guys are representations which should arise from nilpotent orbits and their covers under the orbit method, which hasn't been established for semisimple groups. But at least we have an idea of what should be produced from nilpotent orbits and their covers. All right, so let me finish here.
Thank you very much. So I'm kind of a little bit lost in the logic. So you throw away Harish-Chandra modules because you are talking about Harish-Chandra bimodules. Mm-hmm. So which means that kind of you relate orbits with Harish-Chandra bimodules, and so do you say that this Harish-Chandra modules it's something, some wrong notion or what?
No, it's a perfectly nice notion, but in general it's more complicated. So let me get back to this disclaimer. So we can classify some Harish-Chandra modules over quantizations of nilpotent orbits. In the gel case, unfortunately, I don't think there is a good classification. Maybe because the notion of Harish-Chandra modules that I use is not correct. So somehow, you know, when we talk about Harish-Chandra bimodules over arbitrary quantizations, we get rid of any symmetry coming from the group. It turns out that we don't lose much. But when we talk about Harish-Chandra modules in this setting, I can write down the definition if you want. Then somehow losing this symmetry leaves us with objects that we cannot control. For example, much of the Harish-Chandra bimodule story is controlled with what happens over quantizations of linear singularities. And we have a reasonable classification of irreducible bimodules in that case. I don't know what are irreducible Harish-Chandra modules over these quantizations, at least with the definitions that I'm using, which may be wrong. Nevertheless, when we deal with a classical notion, we can still classify reducible Harish-Chandra modules with this, you know, with maximality of support condition under this assumption here. And let me tell you what this assumption gives us. So first is this. So the codimension of the boundary for the singular Lagrangians is big or equal than 2, which currently I don't know how to remove. But also, so kind of the action, the fight for extension happens on dimension 2 slices. And we are very lucky because in these cases, we know all possible dimension 2 slices. And this dimension 2 slices, well, I mean, in the symplectic setting, they're going to be dimension 4. They're mostly very easy. They are either the closure of a minimal nilpotent orbit in SL3 or in SP4. And then we have full control over Harish-Chandra modules over the slices. So to have control over what happens over the slices is absolutely essential for this business. And so in these cases, we can give a complete classification, and currently it's as good as that's what we got. So you can still talk about Harish-Chandra modules, but the situation is considerably more complicated than bimodules in many respects.
Okay, all right, yeah. More questions? Maybe I have kind of one more question, although again, it's sort of perpendicular to your story, because morally your X has kind of, at least, well, it's probably technically it's wrong, but I'm thinking that it's a sort of a conical singularity, something like that, that is C star, probably, yeah, probably it's wrong, that it contracts everything. You have just one sort of singular point. Anyway, what I mean, that you see D modules when you quantize either the cotangent bundle or the diagonal in X cross X, yeah, like you think of differential operators in terms of kernels. That's okay, but it's everything is local. But there are other Poisson or symplectic varieties, manifolds, when you do have a C-star action, but the picture is not that homogeneous. For example, C-star cross C-star, or C-star in the power 2n. Like this kind of multiplicative, I would say, or rather trigonometric, if you think about this story as rational. And I do not see, for example, a quantization of C-star cross C-star. It's very close to the Heisenberg algebra, which you mentioned in the example. It's just multiplicative version. So quantum torus, yeah. And so you still can ask questions about representations or irreducible representations, but this particular class of examples, it does not fit.
It doesn't.
Into your story.
Because somehow you lose the connection with the connection with the classical guy is much less straightforward, right?
Well, I mean, no. In general, if you have
unless you want your parameter to be formal.
What?
Unless you want your parameter to be formal.
Yeah, this is true. This is true. There is a way, at least in this particular story, to allow the parameter to be non-formal. Yeah, as we know, the quantum torus exists when Q is not necessarily a formal parameter, and there is an independent notion, independent on just mod H bar of the quasi-classical. There is a story about Lagrangian supports. It's more complicated. I think it goes back to that paper of Maxim Kontsevich, when he introduced the notion of P support using sort of a finite characteristic reduction. So, and basically, I think he conjectured that in that story, every algebraic Lagrangian can be quantized without conditions about irreducibility, just some holonomic module over this quantized algebra. Yeah, but yeah. So at least, well, I think that the questions about irreducibility, they can be kind of considered in more general quantization story, not necessarily related to the modules, but as for unitarizability, actually probably they can be considered as well. If the absolute value of this Q is equal to 1, probably they're unitarizable. So that's not everything is realized as a differential operator acting somewhere. Yeah, sure. That's what I mean. Sure. There are difference operators, and it does not fit into this. It doesn't. Yeah. Okay. All right. More questions? Well, if there are no questions, let's thank Ivan for the very interesting talk. Thank you very much.
You're welcome.
And this is it for today.